Today we're going to start a new unit, new chapter, new content. So let's just dive in. As a brief reminder of what happened in the previous chapter, I want you to take a look at this question. There's a couple of steps involved in it. You have to really pick apart the entire problem, but take a minute. You can hit the pause button. I'll count to some reasonable number. I'll get started. I'll pick you up along the way. To figure out the pH, I think the first thing that we need to do is figure out the equivalence volume. And in this case, that's going to be equal to 0.08364 molar times 25 milliliters divided by 0.1067 molar. Which that should come out to approximately 19.60 milliliters. So the question is, we're currently at 4.63. We're going to be in region 1. So this is a buffer. Now we're adding acid to base, and that's why they give you the Kb value to actually calculate the pH. We're going to need, since it is a region 1 buffer, pKa. Pyridine, as far as they can show, there's only 1 Kb, so it's a monoprotic system, and that sounds wonderful and easy to deal with. In this case, it's going to be B over BH plus. At 4.63, instead of figuring out a mole ratio or a percentage, we're just going to subtract 19.60 minus 4.63. And so our pH in this case, the pKa is going to be 5.20. That's, of course, the pKa using the Kb and Kw, plus log of 14.97 over 4.63, which should come out to a pH value of 5.71. But like I said, we're departing from things largely, at least for the first, I'm going to say 2 lessons, maybe 3, of this chapter. So normally I would hand out a reading. It's the reading found, as you can see in the top right above my head, from the beginning of chapter 11. I enjoy these readings. They give you all sorts of information, and it is something that usually gets addressed over the course of the period. And so I would give you a minute to read it, but 1, it's small, and 2, well, I mean, I can just read for you. Specifically, we're going to look at the 4th paragraph. We're going to pull out some information. Hopefully this is going to drive at least this lesson, if not the unit. EDTA. So the reading is about ion channels and how the ion channels can accept sodium but not potassium, or maybe it's the other way around. And it's the idea of unsheathing the metal ions from the water solvent cages that they have when they're in solution so that they can be admitted into the cells through the ion channels past the cell membrane. But EDTA is a merciful abbreviation for ethylene diamine tetraacetic acid, a compound that forms strong one-to-one complexes with most metal ions. We'll see figure 11-1 soon. And finds wide use in quantitative analysis. EDTA plays a larger role as a strong metal binding agent in industrial processes and in products such as detergents, cleaning agents, and food additives that prevent metal catalyzed oxidation of food. EDTA is an emerging player in environmental chemistry. For example, the majority of nickel discharged into San Francisco Bay and a significant fraction of the iron, lead, copper, and zinc are EDTA complexes that pass unscathed through wastewater treatment plants. Funnily enough, don't forget that this textbook was published several years ago. Your project's going to be looking at some of these environmental impacts or real world applications of this compound EDTA, and I will say this with reasonable confidence. There is some food in your house that if you read the ingredient label, calcium disodium EDTA, to maintain freshness, would show up on the food label. It is quite prevalent in our lives, and what's interesting is that you may never have heard of it before, unless, like me, you've read a bunch of food labels. So I learned that metal ions spoil food. That's new. Metal ions can also be trapped and I guess deactivated by EDTA. EDTA, I'm not going to describe it because that's this entire paragraph, but there's a name for it, and it's a compound. It's a chemical that does stuff. Where is it used? Well, like it said, detergents, cleaning agents, food additives, environmental chemistry, and there's probably a couple others where this compound shows up. So what is this and how does it work are the two questions I think I'd like to answer over the course of this. If you've got other ones, by all means, put them in a comment below and I will answer them to the best of my ability. As a brief review, though, key to how EDTA works is a quick discussion of Lewis acids and Lewis bases. Of course, we have our Arrhenius and Bronsted-Lowry definitions, which focus on hydronium hydroxide and transfer protons. But in a much wider sense, the acid-base reaction can be shown through electron pairs. That is to say, if a water were to act as an acid and dump its H+, what you could say is that this shared pair becomes an unshared pair. So really, there's a transfer of electrons from partial ownership to total ownership or partial ownership to no ownership. So we're instead of looking at these Bronsted-Lowry, we're going to look at electron pair acceptors as any substance with empty valence or valence adjacent orbitals. The most common substances that have empty valence or valence adjacent orbitals are metal ions. For example, let's just say sodium. You remember that sodium electron configuration, the 3s1 electron is the electron that gets lost. That means that those three orbitals, the principal energy level 3 orbitals, are empty and relatively energetically accessible. Not super accessible, but accessible enough where, as we've seen over the course of this year, chemistry can happen. And for the Lewis acids to accept an electron pair, some substance has to donate. So we have talked about how metal ions can interact with anything that has electrons, but anything, including an ammonia, including a water, but even including a fluoride ion. Anytime you have these valence electrons, they can be donated in much the same way that we saw that the water dissociating was going from a shared pair to an unshared pair. We can take an unshared pair and turn it into a shared pair energetically, possibly. And this opens the door to talking about a substance that we call ligands. I believe we talked a bit about this in chapter, I want to say 6 or 7. I think it was 6. We're going to just define a ligand as any substance that's going to attach to our metal ion through coordinate covalent bonding, which means by the previous slide, if the metal ion is the acid, then obviously any of the ligands doing the binding are going to show as the Lewis base. And the coordinate bonding, just as a quick refresher, is where both of the electrons that are shared are supplied by one of the two atoms instead of one from each. This really only comes into play when we're talking about things like formal charge, which I'm not going to worry about too terribly much, but just to point it out, the simplest form, one of the simplest forms is boron chemistry, which is fantastic. And what ends up happening is this electron pair gets donated because, of course, boron with 3 valence electrons and maintaining a neutral formal charge needs to only make 3 bonds. If a 4th bond is made, this would actually incur a formal charge of a positive and a negative. And so there's this wonderful balancing act with boron chemistry of formal charge but filled up second energy level versus no formal charge and not quite filled up second energy level. But coordinate covalent bonding does show up a lot in, yes, you have these acid-base processes, but we've also seen it in ammonium ions and hydronium ions. Keep in mind that when we talked about these are substances that were picking up an H plus ion where this lone pair gets donated in. And these ligands show up too. We said molecules that attach to a metal. So instead of H, maybe we remember a couple chapters ago, I think, again, it was chapter 6, that has the ability, we have these iodide ions that we're attaching to lead ions to make these, nope, need an eraser, was doing so well. These metal ions that that attach to non-metal ions, wow, there we go. And remember that they're always in equilibrium. So to expand a little bit upon our vocabulary, we're also going to bring in this term of dentate. This is a monodentate cyanide because it binds to a metal ion through only one atom, the carbon. So again, we've got our Lewis acid, our metal ion. Cyanide has these lone pairs in the carbon. Turns out the carbon with the formal negative, and I'm pretty sure it's the bigger atom. So I feel like those electrons are a little bit more accessible in terms of their electron cloud, can donate in to make these complexes, like I said with the lead iodide that we saw complexing 1 through up to 4 times, making these complexes. And in each case, the complex is always in equilibrium, which means if there's an equilibrium, there's an equilibrium constant. And by definition, we're going to say that these ligands attach to these metal ions, these substrates, in a formation fashion. That is to say that the complex is the product. The complex is always the product. In this case, Kf would be equal to complex concentration over substrate and ligand concentration, all of these being complex concentration, free substrate, free ligand. So there's going to be some of all three of these substances, and in this case this would be the AgCN2 plus concentration. Nope, that's a minus. I know how charges work. Over silver plus, and then it would be times the free cyanide concentration squared. And then you could go through and solve for the math if you had the right value to actually solve that problem. But when we say monodentate ligands exist, well, I mean, that kind of implies that multidentate ligands exist. And so anytime a metal ion will attach to the same molecule, the same ligand, more than once, it would be a multidentate or a chelating ligand. The H is kind of silent. Most transition metals will actually end up having room to bind 6 electron pairs. There's something, crystal field ligand theory. I'm going to put a link in the description if you want to read about it. It says that these d orbitals, especially with these transition metal ions, like I said, valence or valence adjacent, they're sufficiently low enough energy to actually participate in this Lewis type interaction. But in doing so, bringing in the ligand with its electrons, the orbitals that have those electrons nearby actually have a different interaction than the ones that don't. And if you want to get into the geometries of the d orbitals, that means that those that are being infringed upon go up in energy, and those that aren't go down in energy. And there's this big conservation of energy term, and basically what it means is that especially when you have a certain arrangement, that 3 of your d orbitals go down in energy and 2 go up, and these 3 orbitals represent fitting 6 different ligands around your atom. Anyway, an example of what we would call a bidentate ligand would be ethylene diamine. And down here we've got a really brief reaction of how that works, where both of the nitrogens in this ethylene diamine, keep in mind these are both carbons and there are attached hydrogens that are not shown, both of these nitrogens would attach to the same metal. So if a copper ion was to fit 6 different electron pairs around it, instead of fitting 6 monodentates, you could fit maybe 3 bidentates. And the whole reason we're talking about this is that there's actually a difference in terms of equilibrium constants, and we need to pick that apart. The Chelate effect is something that happens when we do introduce several of these multidentate ligands. It turns out that this process is actually more stable. I kind of don't want to get to the why until I show you some pictures, but for example, you have like a cadmium ion or a copper ion, typically surrounded by 6 waters. Like I said, you could trade out 2 of those waters for one of the ethylene diamines. So what we could see is we could see our cadmium, and I'll draw the other ones, but we're not going to fill them in. And we could surround them, right, where there could be waters all around. Or you could have, and keep in mind, like I'm not filling them in, but they would be filled in. I'm just going to save some time in drawing. The 2 wedges that are colored in are coming out towards you. The 2 dashed lines are going back in. So this is an octahedral arrangement. We could have this ethylene diamine where there are H's, but we did just donate these electrons from the lone pairs into a bonded pair. And then we would also, don't forget, have, the C's and associated H's attached out here. So what we have is like this metal ion, and we've got this ethylene diamine flying in, but it's got 2 different electron pairs that can both attach in. Now, what I'm talking about with the chelate effect is the idea not about replacing waters with this ethylene diamine. If you want a direct comparison, the biggest comparison of how well chelation occurs would be to replace this bidentate with 2 monodentates that are chemically identical. And to do that, we're actually going to use a substance called methylamine, which is the same exact molecule, except instead of having a carbon-carbon single bond, you've snipped the carbon-carbon single bond, and instead you got 3 hydrogens attached to the carbons. So instead of having one molecule come in with both pairs of electrons, you've got 2 separate molecules, each coming in on their own. If there is a difference in trading out waters for methylamines versus trading out waters for ethylene diamine, that means that the chelate effect is the reason for it, because the only difference is whether or not these 2 carbons, and I'll draw it in a different color to be less confusing, whether or not these 2 carbons are attached by some sort of bond, and what effect that bond actually has. So let's take a look. Instead of, we've got our 2 reactions, replacing the waters with methylamines and replacing the waters with ethylene diamines, and we can see very different values in the Ks. What does this mean? Take a minute. Seriously, I want you to hit the pause button. Look at the picture. All the data is there. This is a wonderful opportunity to look at and try and tell me why there seems to be a difference. I'll give you one hint before I let you think. Collision theory is not meaningless. So if we want to think about this in terms of a mechanism, the idea is that a water falls off and an ethylene diamine comes in, or a water falls off and a methylamine comes in. For 2 methylamines to take the place of 2 waters, you need 2 collisions, which means you need 2 molecules to work their way over with the randomness that they have. The nice thing about ethylene diamine is as soon as one side of the ethylene diamine attaches, the other one's all flopping around in the background, and the opportunity for it to flop into place is much larger because it's physically tethered with a covalent bond. That drastically reduces the entropy factor because they're literally attached to each other via this bond. So as soon as the first one attaches, this other one flops around for a bit and pops right in. It's ready and waiting, kind of. In this case, when this one molecule pops in, for the next one to come in, it's just random chance for it to come by. The randomness is actually far decreased, and that actually, in this case, shows that because this is 10 to the 9th versus 10 to the 6th, 8 billion versus 4 million, you see that many more ethylene diamines attaching at equilibrium and staying there. That's what the end point is. Another way to look at this, like I said the word entropy. If you'll notice, the products of the top reaction are 5 particles made from 3. 3 particles come together, 5 particles made. Entropically, this is more favorable. The free energy tends towards having the waters liberated and having these 2 ethylene diamines take their place instead of 4 waters being locked up. Now, the reason I talk about all this is EDTA. Ethylene diamine tetraacetate. Ethylene diamine tetraacetate. This image above my head shows what happens when ethylene diamine gets attached to a metal ion. And I want you to take a look at this structure. And if you'll notice on the diagram, if the manganese has 6 Lewis acid receptacles, ethylene diamine seems to be a perfect molecule to address that. You have on the key below that these are all oxygens, that these are our nitrogens. And we know that nitrogens and oxygens have a bunch of lone pairs. Each of these have electrons that can jump in. Even more so, if you've talked about resonance, the acetates have resonance to kind of stabilize it existing as this. And once it attaches, you lose the resonance. But having the 6 sites occupied by one molecule, well, looking at these numbers, if having 2 of them connected increases by 1,000, I can only imagine that the K value for this would be insanely large. And I've included here a table 11.2. This is the formation constants for EDTA complexes with several metals. Again, it's formation constant, so it's going from the separate to the together. And you can see that the equilibrium constant for cadmium, I know that's manganese there, I'm relating it back to cadmium on the previous slide, is 10 to the 16.5. And remember that this says log Kf, not pKf, so don't negate it. 10 to the positive 16th. That is 10,000 times better than just having 2 ethylene diamines, interestingly. So EDTA is this molecule, this hulking large molecule, but it's structurally built to have these Lewis base lone pair electrons spaced 2 atoms apart. And I've noticed this. If you look really closely, there are pentagons between each of the sites. And the reason those pentagons work so well is that those pentagons actually are floppy enough that those lone pairs can get to those 90-degree angles to be octahedrally arranged around your Lewis acid metal ion. And that means that this EDTA has, that's how this works. It's got all of these uses in all these fields because with a constant of 10 to the 16th, EDTA grabs onto metal and it doesn't let go. That's the most important thing to learn from this, that these polydentate materials exist and they are so well suited for binding to metals that they have applications in nearly every industry if you know how to use them. Thanks for watching.